Okay, well, welcome back to asymptotics and perturbation methods. So here in lecture 4, we're going to be discussing a really clever method for estimating integrals asymptotically. It goes by the name of Laplace's method, and it's so tricky and really ingenious. I mean, in a certain place, it looks like we're considering a small epsilon that we then shortly set to infinity. Not quite, but I mean, it might look like that's what we're going to do. But anyway, let me just show you how it goes, and you'll see how ingenious this is. The big payoff from today's lecture is that we will calculate an asymptotic formula for the factorial function, or equivalently for the gamma function, for large values of its argument. And it's this very famous old formula called Stirling's formula, which, like so many things, that have names, it was not discovered by Stirling, was discovered by de Moivre. But Stirling did contribute something by calculating a certain prefactor that comes up in the formula. Anyway, so let me jump in. Here we go. Share my iPad. All right, so Laplace's method. There's a lot of writing in this lecture, a lot of calculations. So I did write out some stuff ahead of time, but mostly I'll be showing you the details, in real time. So anyway, if you want to read about this in Bender and Orsag, it's in section 6.4. And it's a method that applies to what we could think of as sharply peaked integrands. Think of something that looks bell-shaped, but with a very narrow bell. That's what we mean by sharply peaked. And what's nice about these sharply peaked integrands is that the dominant contribution to the integral comes from the bell, the narrow part of the bell. The dominant contribution comes from the neighborhood of a single point. And so when I mentioned epsilon, what we're going to be thinking about here is in the limit as some parameter becomes large, for us, it'll typically be this quantity we call x. As x gets large, the width of the bell will get narrower and narrower. And so we'll be focusing on that epsilon neighborhood of the maximum. All right, so here's a quintessential example of such a thing. Literally take a Gaussian, the bell-shaped curve, e to the minus x t squared, where x is playing the role of, I guess it would be like 1 over the standard deviation squared. More or less. So as x gets large, this bell curve gets narrower. And the thing that we're going to do that's a bit strange is we're considering the integral from minus 10 to 10. Now, if it were from minus infinity to infinity, that's a known integral that you can do. You would have seen it in courses in probability or statistical physics. We could do the integral exactly if only those limits were infinite. But let's suppose they're just minus 10 to 10. So this integral is of the form that we discussed at the end of the last lecture that we call the Laplace style integral, that involves a continuous function f times an e to a large parameter x, and then some other continuous function phi of t up there in the exponent. And remember, we were analyzing that with integration by parts, but we pointed out that there was a way that integration by parts could break down, which was if the function phi had a derivative equal to 0 somewhere in the interior, then you couldn't use integration by parts. You'd end up dividing by 0 at some point. So this is exactly of that type, because the function phi for us here is this t squared, which does have a derivative equal to 0 at t equals 0. And so we can't apply integration by parts, which is fine, because in fact, the asymptotics of this are not controlled by integration by parts. You may remember that when we had integration by parts, we were getting expansions in inverse powers of x. We had like 1 over x, 1 over x squared, things like that. That's not going to be the case here. We're going to end up getting a fractional power of x. So integration by parts couldn't possibly work. All right, but anyway, so this is the integral we want to consider. And as I say, notice that phi prime of t is 0 on the interior of the range of integration. So no go for integration by parts. Now, if you didn't know how to do this problem, you could very crudely estimate it like this. Draw the bell curve. I've drawn it in blue there. And then just think about it in terms of its width and its height. So you could say it has a height of 1. And its width, well, the characteristic width is this quantity here, 1 over square root of x. You can see that because, like, think what it would take for this argument of the e to be order 1. That will happen when t is 1 over square root of x. Another way you could see it is you could ask, when does this quantity drop down to 1 over e? So e to the minus 1 would be achieved when xt squared is 1, and that's when t is 1 over square root of x. So anyway, this is a characteristic width sideways of the bell. And then pretending that the whole thing is a rectangle, like I said, it's crude. I mean, the width scales like 1 over x, 1 over square root of x. So treating it sort of as height times width for the area underneath, you would expect that the total area underneath, namely the integral, should be of the order of 1 over square root of x. And that's going to turn out to be correct. But what Laplace's method will do for us is give us the prefactor, the constant, not just the scaling. All right, so let's now calculate it. Here's the idea. Think about regions that are sort of out here. The stuff out in the tail, or if you want over here too in the tail. The tail is going to give us exponentially small contribution to the integral. That's the main idea compared to what we have under the bell. So in particular, the region where t is much greater, let's say in magnitude, than 1 over root x. So these are the tails. They contribute, that region contributes exponentially small terms. In fact, in the language that we used in lecture 3, or I guess it was lecture 2, we talked about asymptotic approximations had this inability to detect what we called transcendentally small terms. Those were terms that are decaying to 0 much faster than say inverse powers of x or something like that. So these transcendentally small terms, which I abbreviated TST at the time for transcendentally small terms, these transcendentally small terms don't affect the asymptotic approximation. So we don't even have to pay attention to what's happening in the tails. They're going to contribute terms that are negligible anyway. So that's the insight in Laplace's method, that the tails will contribute these transcendentally small terms, and these will not affect the asymptotic expansion. So, I mean, they are going to be, these terms are subdominant in the jargon of the Bender and Orsag book. They are subdominant to the integral I of x itself. So, in lecture 2, we sort of worried about that, but now we're going to exploit that. That's going to be a beneficial thing because it means it's sort of like pocket change. You can throw in transcendentally small terms or delete them or whatever, and it doesn't make any difference. So here's how it goes. Let's take I of x that we're interested in, it's the integral from minus 10 to 10 of e to the minus x squared, e to the minus xt squared dt. And we're now just going to assert that that is equal to extend the range of integration out to infinity. And we've made a mistake that is transcendentally small by doing that. Because all we did was add in the tail contributions. And the beauty of making this move is that we know how to evaluate this integral. This is a famous Gaussian integral. This is something that's taught in multivariable calculus. So I'm going to assume you know there's a certain trick using polar coordinates. Not going to go over that, but you can either solve this integral with that trick or with using gamma functions. Anyway, this is a known integral. You could just ask Mathematica to do it if you don't know those tricks. Anyway, this is exactly solvable, and it comes out to be pi over x square root. And so that's our asymptotic expansion of I of x. We don't have to pay attention to the transcendentally small terms. And notice, by the way, that this is of the order of 1 over square root of x, as expected by the naive argument, the crude argument. So you see what we did. We focused on, I mean, this is all in the limit as x is going to infinity, that the tails are negligible. So that's basically the strategy in Laplace's method. But of course, this was an extremely simplified example. I'm going to do a more, actually, I hope to do 2 more complicated ones in the rest of the lecture. One thing that may be slightly worrying to you at this point is how do we really know that those terms are transcendentally small? Let me just do that estimate for you in case you're wondering about that. Let's just quickly dispense with that. To check that the remainder terms really are TST. Here's one way we could think about it. So observe that the integral of interest from minus 10 to 10 is the integral from, these all have the same integrand. So from minus infinity to infinity, and then minus 2 times the contribution from the tail. So say from 10 to infinity of e to the minus x t squared dt. And so let us try to understand, we want to bound the size of this tail contribution. So what's an upper bound on that? Well, so if we're going from 10 to infinity, I mean, the slight difficulty here is we don't know how to do that integral exactly. It doesn't have a nice indefinite integral. If you know about error functions, you could do it that way. But suppose we're just working in the world of elementary functions. We could do the estimate this way. This can be bounded above by observing. Well, let's just look at the function t squared, because that's what's causing us the trouble. If that t squared were a t, we would know how to do the integral, the indefinite integral. So if I compare t squared to, let's see, we're in this region where t is greater than 10. Right, that's where we're interested in. The tail is from 10 out to infinity. So if I think about what's happening at 10 and beyond, I could compare this curve to the straight line that goes through. This was supposed to go through there. So this is the line 10t. And what I'm noticing is that t squared is greater than 10t. when t is greater than 10, right? The parabola lies above the straight line, clearly. And so how does that help us? That tells us then that if I put negative signs in front of those, that minus xt squared is more negative than minus 10t. Right? In that sense, it's less than, it's more negative. And so that means then if I take the exponent, the exponential e to the minus x t squared, since e is a monotonically increasing function, this bound is true. And so I'm now in a position to get an upper bound on my integral by just saying, I can estimate the tail by saying that this is less than the integral e to the minus, oh, did I forget an x? I did. Let me put the x in there. X. 10 x t dt. And that's a perfectly nice integral that we can do. We get e to the minus 10xt all over 10x. And then I have to evaluate it between t equals 10 and t equals infinity. So that boils down to saying that this tail is less than, substituting t equals 10, I now get e to the minus 100x. That is one heck of a small function, divided by 10x. And as advertised, this term is exponentially small. It's got this e to the minus 100x going on in there. And so this is way, way, way smaller than anything of order 1 over square root of x. There's no problem. So this is what I'm saying, that this rigorous bound on the tail is subdominant to the our estimate of the integral itself. So let me pause there. Is there any questions so far? Okay. This is not a very impressive example because it's not a super interesting integral. But now Laplace's method shows its stuff. When I start getting into this monkey business I was talking about with the epsilon, going to 0 and then going to infinity maneuver, if we do a little more serious example. So let me do one of that type now. Okay, so let's try this one. I of x is integral from minus infinity to infinity of e to the minus x hyperbolic cosine of t, so cosh t dt. And that cosh is sitting up there in the exponent. So remember, cosh is something that is itself growing exponentially. Looks sort of like a parabola, except it's growing exponentially rather than quadratically. And then that's sitting up there in the exponent. So if we were to graph the integrand, looks sort of, let me try this again. So the integrand looks approximately bell-shaped still. Because remember, cosh t, if you sort of pretended cosh t was like t squared, well, it isn't really, but for small t, it behaves like 1 plus t squared over 2. So this thing sort of has the feel of some bell-shaped curve, except it's a little different from our previous example. So this is as a function of t, in that this height is no longer order 1. This height is now e to the minus x. Right, because when t is 0, cosh of 0 is 1. And the width, well, it still has the same property that the width is going to be, I think, like square root of x, 1 over square root of x. We could check that. So this is going to get narrower as x gets large. And what would happen as x gets large is not only does it get narrower, but it also gets lower. So you'll have something like this at larger x. Right. It's coming down in height and it's also shrinking in width. So we want to estimate the area under this with these two things going on. Okay. So let's do the leading order asymptotics first, and then I'll show you how to get the full asymptotic expansion, every term in the asymptotic expansion. All right, so first, just the main term, the leading order. Well, to do that, it's okay to approximate cosh in the neighborhood of its maximum by saying cosh of t is 1 plus t squared over 2 as t is going to 0. Because I'm thinking, remember, of a very narrow bell. When this blue curve is very narrow, I'm focusing on what happens in the neighborhood of t equals 0. So I'm just going to use that very simple Taylor approximation. And so here's where I'm thinking about the epsilon neighborhood of 0. That everything about the asymptotics is controlled by that epsilon neighborhood of 0. So if I do that, well, I mean, you might be thinking to yourself, this is ridiculous. Cosh of t is not quadratically growing like this. We know it's exponentially growing. So it seems like I'm making a terrible mistake by using this approximation. This is only valid for small t. What about the larger values of t? But that's the thing. At larger values of t, the integrand is exponentially small. So we don't care about that stuff. When t is large, the approximation that we've just made is not so good. So this approximation is not so good out there, but it doesn't matter. That's the cool insight. The approximation is no good out there at large t, but it doesn't matter because that part of the range of integration is only contributing transcendentally small terms anyway. Since the integrand is exponentially tiny out there, again, for large x, so exponentially tiny out there for moderate t or large t, and contributes only TST, which we don't care about anyway. So that's the strategy then in Laplace's method, that let me replace cosh of t by its simple Taylor approximation, its Maclaurin approximation. And so then I would say my I of x will be asymptotic to, well, I was supposed to go minus infinity to infinity, e to the minus x. I'm replacing cosh by 1 plus a half t squared dt. And then I know how I've now boiled it down to doing Gaussian integrals again. So I can factor out the constant term e to the minus x, that's constant with respect to t. Then I have a Gaussian integral e to the minus x t squared over 2 dt. And as before, I'm assuming we know how to do those. And so that's going to give me square root of 2 pi over x, and then times e to the minus x. That's my asymptotic approximation of the integral. So it's kind of wild. I mean, if you think about what we were doing, we focused on the epsilon neighborhood of t equals 0. I mean, really, maybe I should have thought of it that way. I wonder if this is a little clearer. If I had said only the epsilon neighborhood matters. So think of it like that. It's the epsilon neighborhood, and there it was okay to replace Cosh by its Maclaurin series. But then I formally think of saying, let epsilon go to infinity because it only contributes transcendentally small terms. Right? I mean, that's the missing step, that this is asymptotic to the integral from minus infinity to infinity of the same thing, plus the fact that I added in a tail error that gave me transcendentally small terms. So that was the reasoning. Okay, so that's an example. Now, that only gave us the leading order term. You might be wondering, what if I want the full asymptotics? And so here's how you can do that. This is where it really starts getting fun. Let's do higher order. I mean, what's so amusing is that the higher order terms are also controlled just by this epsilon neighborhood of the max. So here's one method for getting them. We saw that how helpful it was to think of Cosh and replace it by its Maclaurin approximation. Let's now do that, but in a more exact way. This motivates an exact change of variable. Where I'm going to define a new variable tau such that Cosh of t is exactly equal to 1 plus this new variable tau squared. I mean, the point being, we've seen how helpful it is to have Gaussian integrals. And so by force, I'm just going to make sure that I have one by defining a tau squared in here, so that when I replace e to the x Cosh t by the new variable, I'm going to get an e to the x tau squared. So I'll just force the Gaussian integral on the problem. This is no big thing. All I'm doing is just defining tau squared equals Cosh t minus 1. So regard this as a definition of tau. It's simply Cosh of t minus 1, square root, I guess. So there it is. I'm just going to make this substitution and watch what happens if I do that. I'm going to then convert everything to a tau integral. So make the change of variables indicated here. What do we need to do? We need to replace the dt by something involving d tau. And so to do that, take the differential of both sides. And so I would get sinh t dt is 2 tau d tau. And so that's giving me a formula for dt in terms of tau, which is dt is 2 tau d tau divided by sinh of t. But now I want to express sinh of t in terms of tau. So I'll use the trig identity, or the hyperbolic trig identity, which is what? How does that go? It's Cosh squared minus sinh squared equals 1. Right? It's like cosine squared plus sine squared, except as a negative sign. So Cosh squared minus, all right, so that says sinh then is going to give me what do I need to do? It's cosh squared t minus 1, right, is sinh, square root. So cosh squared t minus 1 square root. So in other words, it's 2 tau d tau over, so cosh we defined as 1 plus tau squared. So I go 1 plus tau squared, that's all getting squared, minus 1 underneath in the square root. So that can be simplified a little bit. That becomes 2 tau d tau over, so expanding the square in there, we're getting what is that? So I have 2 tau squared plus tau to the 4th. Inside the square root, so I've done my algebra correctly. And so it's sort of desirable to factor out a square root of 2 tau from that whole thing. So 2 tau, d tau, take out a square root of 2 tau, just like your high school algebra teacher would make you do. And then, see, now you know why you had to do that in high school. So you could do Laplace's method. And then 1 plus tau squared over 2 in there. And so, oh, wait a second, I did that wrong. I need to go like that. These taus cancel out, right? And so I end up getting, if I've done it right, yeah, I think what I'm getting is a square root of 2 on the top, d tau, all over square root of 1 plus a half tau squared. So what is all that? That was just what I needed to do to change variables for dt. Okay, so putting everything together, we've now converted the integral. So the I of x that I'm interested in is equal to, with this change of variables, it was e to the minus x cosh t dt, but now with the change of variables, it's e to the minus x 1 plus tau squared. That was our clever move in the cosh. And then the dt was the painful part that we just calculated to be square root of 2 all over square root 1 plus a half tau squared d tau. I think I've done that right. So I can now factor out the stuff that doesn't depend on tau. So there's a square root of 2, there's an e to the minus x coming from that one term in the exponent. And then the rest is the stuff I'm going to hit with Laplace's method. So there's an e to the minus x tau squared d tau, and then a square root 1 plus a half tau squared. Yep, there. So that's exact. We haven't done any asymptotics yet, right? This was just a clever change of variable. Want to ask anything about the manipulation so far, or you followed all that? Okay. All right, good. Yes?
I'm a bit confused about the bounds. So
The bounds.
is infinite when you go to minus infinity and plus infinity. So when you want to solve the condition at infinity, we have two solutions from tau. So why don't you choose on the other one?
Yeah, it's interesting. Let's think about this, right? So if you're concerned here, I think of it as tau running from mine that, I mean, this, maybe it's helpful to visualize it. Let's see how to say this. Because I did do one little shady thing. Maybe you caught me while I was doing it. I didn't comment on it. I mean, cosh looks qualitatively like this as a function of t. And so I'm trying to replace that with this 1 plus tau squared, where I'm sort of reparametrizing the t-axis into tau. It's like a nonlinear distortion of t into tau, so that this shape is now 1 plus tau squared when I've redefined my real numbers, so that t is mapping to tau, right? That is, I want to visualize this thing as both 1 plus tau squared and also as cosh t. And so it's really the case that minus infinity for tau corresponds to minus infinity for t, and plus infinity for t corresponds to plus infinity for tau. So it's really just a slight warping of the, I mean, pretty violent actually, taking something algebraic into something exponential, but it's some kind of distortion of the t-axis. But it is keeping infinity at infinity and minus infinity at minus infinity. Now, the thing I did that was a little shady and that my high school algebra teacher used to correct me on was when I took the square root of tau squared, I should have really written absolute value of tau, shouldn't I? That's really what you're supposed to write. But then I started getting myself confused if I did that, because I know that this expression I've written is correct. So I don't know. I mean, we could go like from 0 to infinity and not have to deal with negative numbers. I don't know. This has to be right. I'm sure this is right. But I'm a little confused about how I did it algebraically.
We can take 2 times and then from 0 to infinity, right?
Yeah, if you take 2 and go from 0 to infinity, then it's all good. So that's why I know it's right. Anyway, so this is all exact. But now here we get, let's come back to doing Laplace's method. What do we do? So what are we thinking? As x goes to infinity, I mean, this is the first time we're invoking x going to infinity. So as x goes to infinity, we know that this exponential term, the e to the minus x tau squared, is a bell curve that's getting more sharply peaked around tau equals 0. Sharply peaked in the sense that its width is going to 0. About tau equals 0. So, and everything outside that sharp peak, we know is going to contribute transcendentally small contributions. So we are going to expand that square root in the denominator using the binomial expansion. This is the move you always do in these Laplace method problems. You get some function multiplying your Gaussian term, and then you do a Taylor series about the maximum of everything other than the Gaussian term. So I'm going to Taylor expand I'll just write the Maclaurin series. For the 1 plus a half tau squared to the minus a half. I mean, I'm doing a binomial expansion, in other words. Write the Maclaurin series for that and just substitute it in there. Now, this is where, you know, those of you trained in rigorous math will be a little nervous, because this binomial expansion doesn't converge unless a half tau squared is less than 1 in absolute value, right? So this converges if and only if a half tau squared is less than 1. So in other words, tau has to be between 2, square root of 2 and negative 2, a negative square root of 2. But I'm trying to integrate over the whole real line, minus infinity to infinity. Nevertheless, I'm going to just pop the Maclaurin series in there, even though it doesn't converge outside that interval. And the reason is, outside that interval, I don't care, because that region is only going to contribute transcendentally small terms as x goes to infinity. So this is the thing, there's no need to worry about the fact that, I'll say it more precisely in a few minutes, but the fact that the series doesn't converge over almost all of the domain is irrelevant for the asymptotics. So let's just do this, and then I'll come back and revisit this point of rigor. So I'm claiming that I can just say that the result I'm going to get by just substituting in the non-convergent Maclaurin series is I'll still get an asymptotically correct result. So the prefactor square root of 2e to the minus x. I put in the Maclaurin series. Well, let's first put in the Gaussian term e to the minus x tau squared minus infinity to infinity. And with gleeful abandon, I now write the Maclaurin series turns out to be 1 minus tau squared over 4 plus 3 over 32. So here you have to just remember the binomial series or ask Mathematica to do it for you or whatever. So you put in terms like that, and this whole thing is d tau. And then notice those are all Gaussian integrals. They're all of the form tau squared or tau to the 4th or some even power of tau times e to the minus x tau squared. We can do all of those exactly. So I could remind you how to do them if you've forgotten how to do these, or maybe, in the modern era, you would just do them all in the computer. So I'll just tell you what the answer is. If you want, I can briefly remind you how to do them if you like doing stuff by hand. So we'll get square root of 2 e to the minus x, and then these integrals come out to be 1 minus, sorry, there's also a factor, wait, I'm going too fast. When you do it correctly, you end up getting a factor of 1 over square root of x from all the Gaussian integrals. They each contribute a square root of x down here. And then there are additional terms that look like 1 minus 1 over 8x plus 9 over 128 x squared, etc. In other words, I'm cranking out the whole asymptotic expansion. I can go as far as I want. Let me compare that to what we had earlier. What did we have? I mean, is this term right here actually what we saw, square root of 2 over x e to the minus x? I don't remember.
Don't we need a pi?
Yeah, where's my pi? Ah, right, there should be a pi, and that's because I've forgotten it. Right, all those Gaussian integrals do contribute pi's. So that pi is sitting right here. Yeah, I just copied wrong from my notes. Should be square root of 2 pi. That's all inside the square root. There. There, that's correct. So pretty nifty. Right? I mean, you can just generate as much as you want in the asymptotic expansion with this one little idea. So I guess there are two little things remaining. I mean, one is if you want reminding about how to do the various Gaussian integrals, I'm not sure that's worth our time. Maybe I should come back to that at the end if you want to see it. But I do want to comment on this little point of rigor. I mean, what really happened here? How did this work? So it seems like we did this, you know, classic physicist or applied math style witchcraft. So when we're expanding 1 plus a half tau squared to the minus a half, that really is okay. It converges, as we pointed out earlier, when the tau is in magnitude less than square root of 2. And for tau greater than that, it's true that the expansion diverges, but it does no harm. Because each integral that results is transcendentally small compared to the asymptotic expansion itself. We could estimate those carefully if we want, but I mean, each term contributes something that's invisible anyway. Because of the crushing exponential decay that's multiplying those terms. So that's the argument. And, you know, it can be made rigorous. There's nothing fishy about what I'm saying, even though it might seem questionable. If you really want a more careful argument, these steps can be rigorously justified by something called Watson's lemma. Or by the proof of Watson's lemma. Which you can find discussed and proved in the book, Bender and Orsager, on page 263. So they give a precise statement, but at the level of the mechanics of the manipulations, everything I did here was essentially Watson's lemma. So yeah, I'll let you refer to the book if you do want to see a more careful proof. But I don't think I want to dwell on that because I want to try to get to this final example that I really think is a very satisfying payoff, which is a derivation of Stirling's formula for the gamma function. So I guess I will pause there, though, in case anyone wants to bring anything up. Okay. So let me move on then to that. Okay. All right. Well, so here we were doing an integral that involved an e to the minus x times something. And these same ideas can be generalized a little bit to this broader class of Laplace integrals. So we can use these ideas on what the book calls Laplace integrals of the form some function of t, continuous function of t, e to the x, some other continuous function of t, dt, some interval a, b, and in the limit as x is going to infinity. So it's a slight generalization of what we did in that we now have an f of t floating around in front. Okay, so the example then that I want to use these ideas on next is to obtain Stirling's formula for gamma of x. Actually, it's a little more convenient to do gamma of x plus 1, which I think gamma of x plus 1 is just x factorial when x is an integer. As x goes to infinity. So this really is very handy because in a lot of parts of physics and probability theory, you have to deal with factorials of very large numbers, and they're unwieldy to calculate by just multiplying lots of numbers together. But this will just give you in one shot the estimate of how big x factorial really is. Okay, so the gamma function, let me remind you, if we look at gamma of x plus 1, that's the integral from 0 to infinity, t to the x, e to the minus t dt. That's our definition of the gamma function. And it's at first sight not obvious how we're going to apply Laplace's method to this. Remember, Laplace's method is for sharply peaked integrands. Just eyeballing this, you don't see anything that looks like a Gaussian factor in there. It's not so clear that this is sharply peaked. In fact, it's not even obvious where it has a peak. So where is the peak of the integrand? You know, or whether it becomes sharply peaked. It referring to the integrand. As x goes to infinity. So to clarify things, we're going to use a lot of tricks on this problem. I think I count 5 of them. And they're fun, they're clever. You'll get to use them in other problems. And if you're doing the homework, you'll get to use them there. But so the first trick is, well, t to the x looks a little weird. It's usually nicer to work with exponentials involving e. So let us write, so let's call this trick number 1, not much of a trick. Trick 1, right, t to the x is e to the x log t, natural log of t. And then, so in those terms, then gamma of x plus 1 becomes integral from 0 to infinity, e to the x log t, e to the minus t dt. And so now you can see actually that this is Laplace form. We spoke about the Laplace form of an integral, and this has that form in that this thing plays the role of the f of t, and this term is playing the role of the phi of t. So it is in the desired form. Okay, that's good. Now, what about where's the maximum of the integrand? Right, so that's the thing that Laplace's method wants us to focus on, the neighborhood of the maximum, and approximate what's going on around that maximum by a Gaussian. That's always the strategy. So here, the max of the integrand occurs where, well, if you think about it, the integrand is just e of something. We could put it all upstairs in the exponent of the e. So where that exponent is maximized is where the integrand is maximized. In other words, it's where x log t minus, whoops, where x log t minus t is maximized. Now, that's an easy thing to figure out. Where is that maximized? Well, let me use the fact that its derivative with respect to t is 0 there. So d dt of x log t. Think of x as a constant here. So this would be the candidate for where the max would occur. We have to check that it really is a max and not a min. But anyway, that derivative equals 0 when x over t minus 1 equals 0. In other words, when t is equal to the parameter x. So what's interesting about this is that unlike our previous examples where we had t equals 0 was where the maximum of the integrand occurred, right? The bell was always centered at 0. Here, the bell is centered at x, and x is a parameter that's moving out to infinity. So this is what's called a movable max, or a moving max. The max is itself dependent on x. I didn't show it's a max yet, but it is. So the location of the max depends on x. All right, well, that's slightly annoying. And often in math and in physics, when something is moving, it's good to pick a coordinate system where it's not moving. You know, go into the co-rotating frame or co-moving frame or whatever. And so here, let's just make a change of variables that is going to put the maximum in a fixed location in this new coordinate system. And so a good convenient way to do it is to fix the max at one place in some new coordinates. Let's define a new variable, s, equals t divided by x. So I'm going to replace t with s, so that the virtue is that now the max is always going to be at s equals 1, no matter what x is doing. We're only thinking about x being positive here, but okay. So let's see what happens with that change of variables. That is, we're going to replace t by sx. All right, so then that was trick 2, by the way. Sort of really just good hygiene, you know? I mean, if you're good at math, this is the kind of thing you would do. So not really such a tricky trick. All right, anyway, so with this change of variables, then our gamma x plus 1 is integral from 0 to infinity. It used to be e to the x log t, now it's e to the x log sx. And then where it used to say e to the minus t, that's now e to the minus sx. And what used to be dt is now x ds. And so let's clean that up a little bit. So the log s times x contributes 2 terms. One of them ends up coming outside as a factor. So the e to the x log x just provides an x to the x. Then there's inside the integral an e to the x log s and minus s, all in the exponent. And then actually, there's still this factor of x over here. So I might as well group that factor of x in with these guys. And so let me modify what I wrote to make it x plus 1 in the exponent. So this really should be, let me zoom in, x plus 1 ds. Okay, so far? We're just massaging our gamma function into a form where it can be pounded on with Laplace's method. So now we've got our max fixed at s equals 1. Maybe this is a good time to confirm that it really is a max. I guess I want to do that by doing some curve sketching. So here's some more first-year calculus coming to fruition. Actually, let me think of it this way. So I'm going to draw a few functions. Here's what the log, this is a function of s. Natural log, let me not commit too much here. I think I'm just going to, what I want to do is sketch log s minus s, the thing in the exponent, this term right here. I want to understand what that looks like. So I'll do that by just tentatively drawing in some dotted curves of familiar things. Here's the natural log doing its lazy walk. It goes through at s equals 1, goes through the axis there. The function negative s looks about like this. The graph of negative s is like that. And then I want to add those two together. So adding the two curves, let me do that in another color. So I would take, well, let me look at where the log goes through 0. So this is a point on the curve because it's 0 plus whatever that number is, which is negative 1. Actually, I might as well record that, shouldn't I? That's negative 1 right there. And then asymptotically for large s, whatever the resulting curve is, it has to be dominated by, we know that linear things are much stronger than exponential. So the curve is going to sort of look more or less like the line over here. But then when the line is very close to 0, the curve is going to be dominated by the logarithm, but it's getting a negative contribution, right? Meaning adding this negative number to this negative number. This small negative number makes this a little more negative. So what I'm arguing is it's going to look qualitatively like this. It hits its max here, and then it comes around. So that's a sketch of log s minus s. And I'm doing that because I wanted to make the point that it does have a maximum at s equals 1. So cool. By the way, near s equals 1, it behaves like 1, or sorry, negative 1, I guess I should say. Let me put it this way. Negative 1 plus, it turns out it'll be 1 minus s squared over 2. What I'm doing here is writing the Taylor expansion around s equals 1. So I'm approximating this curve by its best fitting quadratic approximation. Right, that's what the Taylor expansion does for me. And I want that quadratic term because that's what goes into Laplace's method so that I get Gaussian integrals. So this was trick number 3. As always, in Laplace's method, you want to expand around the maximum. So we just did that. By the way, you might want to see what does the function itself look like. This was just, I mean, remember, why are we looking at this object log s minus s? The log s minus s was sitting up here being multiplied by e to the x. So I really ought to look at what the whole integrand is, how that's behaving. And so I'm going to sort of draw down here that the whole integrand itself, kind of sketching, continuing down like this. I mean, this is really old school. You would, any sensible person would just do this in MATLAB or Mathematica. But I'm claiming that the resulting integrand is this very sharply peaked object here. That's getting very narrow as x gets large. And you can see what its height is. The height is occurring here. This is all happening at s equals 1. We said at s equals 1, we're getting a negative 1. So this is behaving like a negative 1 times x in the exponent. This term is e to the minus x is the height. And the width is going to do our usual 1 over square root of x, as in all these Gaussian cases. So gets narrower, meaning more sharply peaked as x goes to infinity, with a width of the order of 1 over square root of x again. Okay, so it's doing everything that Laplace's method wants. And so the integral that we're dealing with is x to the x plus 1, integral from 0 to infinity, e to the x, log s minus s ds. And I'm now arguing that that is asymptotic to x to the x plus 1. And I'm just going to replace the log with its Taylor expansion. E to the x, sorry, negative x. And then that expansion was 1 plus 1 minus s squared over 2, all sitting up there, ds. And I don't take any additional terms. I don't need them to just get the leading order. So at this point, well, let me factor out a little bit. I'll take out that e to the minus x. Zero to infinity, e to the negative x times 1 minus s, all squared over 2 ds. And do you notice something weird? I mean, look at how off-center that integral is. It's centered at s equals 1, but the limits are 0 and infinity. So that's not looking good. We don't like that. We want to do a Gaussian integral, but you know the drill. There is no harm in going all the way out from minus infinity to infinity because it only contributes transcendentally small terms. So we're going to center it by just adding in those tails that don't do anything anyway. So that's trick number 4. We can't do this integral conveniently. But it's okay. But we can do it if we add in transcendentally small terms and do the integral from minus infinity to infinity instead. Right, cannot do the integral as written, but we can do it if we add in those tails on both sides. So if we do that, then it's an easy Gaussian integral, and we end up getting our usual factor with the square root of 2 pi. So I have x to the x plus 1, e to the minus x. And then this integral comes out to be square root 2 pi over x. And that is the leading, I mean, we have now written down Stirling's formula. That's it. That's the one-term version of Stirling's formula. So that's the traditional version that you'll see used. And as I say, it was Stirling who discovered the square root of 2 pi aspect of it. De Moivre had all the functional dependence on x, but didn't know the prefactor. So fantastic. This is an asymptotic expansion of x factorial as x gets large. But I want to finish the last 4 minutes here by showing you how you could get the higher order corrections if you were that kind of person. And because I had a feeling I'd be running out of time, I wrote this out already. I didn't know how much space it would take, so as you can see, I left a lot of room. So here's how you could get the higher order terms. Let me just blow through it with you, and you could read it slowly when you have time. But I think you'll get the idea now that we've done the strategy. So inspired by what we saw, that the Taylor expansion was so valuable, let's do that same move we did on problem 2 by doing another trick where we define a variable tau by this exact change of variables, where we introduce a tau so that s minus log s is 1 plus tau squared. That's our definition of tau squared. So it's in the same spirit. We're just manually making sure that we get a Gaussian integral. So doing that, then I have tau squared is, just solving for it, s minus 1 minus log s. And it's looking a little bit unpleasant because to change variables into tau, as opposed to s, I need to solve for s in terms of tau. Right now I have tau in terms of s. I have to invert. And, that's a little bit daunting, but not if you use computers. So we're going to invert this power series to find s in terms of tau, as I'm going to need to change everything in the integral. So using Mathematica, it knows how to invert power series. By the way, Isaac Newton knew how to do this too. When you look at his old papers from, when he was writing letters to Leibniz to teach him a lesson, Newton knew how to invert power series by hand. But anyway, with Mathematica, we can crank it out and we get this formula that s is this power series in terms of tau. That lets me calculate ds in terms of d tau by just differentiating or taking differentials term by term. And so when I then want to do my integral, this is the exact formula for the gamma function. I can now substitute for log s minus s. That becomes, there's a tau squared. I also get this factor of e to the minus x coming from it was really 1 plus tau squared, right? Was supposed to be log s minus s. Anyway, so that gives me my Gaussian term. Here's my ds being converted into this thing in terms of d tau. That's this expression above. So I've got that. And then when I do this integral, I can observe that anytime I have an even power like tau to the first, an odd power like tau to the first power, since this integrand or this term is even in tau, and this is odd, and the whole interval is symmetric, those odd powers of tau will not contribute anything. They're going to be exactly 0 by symmetry. So only the even powers of tau contribute. That's what I'm saying here. And then you just have a bunch of Gaussian integrals to do, and cranking them out and dealing with the algebra, you end up getting this magnificent formula. So this is Stirling's formula with the correction terms built in as high as you want to go. Okay, I'm glad I wrote that out ahead of time. All right, and we are out of time. So I hope you enjoyed that as much as I did. And next time I will show you some more wizardry from the world of asymptotics. Okay, thanks.